here's some of the background into the question, and we have the calculator answers down here at the bottom, which are correlating with the top in terms of their position. So you can see obviously the top left now. The first and foremost way of dealing with the series is through a calculator, and the calculator has if you have a Casio, one of the latest ones, and as you know I really like the FX991EX, then you'll have a button on there just above the on button, which looks a lot like, well, in fact the button is an X, and then above that is a sigma notation, so it's like this, and then it has boxes, some open boxes, and then a square coloring. So what you do is you press the shift button, and then we press the button here, the square button, and this will then open up a template, and you can put the values in just as you see them. And if you need to use a particular variable, like in our situation is R, but you just use the X button in place of the variable. The other one thing to consider is that when you put the number into the bottom of the sigma notation, you don't put R equals, you just put it in as a number, so like number 2. So that's the first way if you have access to a calculator. But if you don't have access to a calculator, then the way you're going to proceed is through sort of breaking it down perhaps. And a lot of it all comes from what happened with Euler. And this little story is that one day he was told to add all of the numbers from 1 to 100 as a punishment. And to be honest, like, until you try and do that, it's hard to appreciate. So let's see, like, as we go along, even writing it can get laborious, to be fair. So let's say you write this cumulatively, you've got 1, and then you've got 3, 6, 10, 21, 28, and you'll soon see that the sums get either very slow because there's so many of them, or you've run out of ability to do that in a time that you're happy with, and so there must have been a quicker way of doing it. The story goes that, thinking about it so long, or maybe even just luckily an epiphany, they thought, okay, if I'm going to add all of these up, I keep going all the way from 1 to 99 to 100. How can I level this playing field? Like, I don't know what was going on in this person's head. Maybe they thought, well, what if I just add them up backwards? Like, I could have done it that way. And maybe even just trying something silly like that, like for just silly reasons, could have come up with the solution or the methodology. But we'll see what happened when they did this. They realized that actually all of these, if you put them in line, they're all in pairs, and they all add up to 101. And once you understand this, like, intuitively, you're probably going to see it all the time, and you don't need to go through this whole proof, but it's pretty clever when you see it. How many 101s have you got? Like, you've got the number that you're adding to, right? So if you generalize it and say that this is n, it's like a whatever, you can have a formula. But let's take this a little bit further and finish it. If you've got 100 101s, but then that meant you added those up too many times, like there should be half, then without a calculator, it's pretty straightforward to do multiply by 100, and if you divide it by 2, then it's pretty easy to divide 10,100 by 2, so we get 50. And you can see that method there, if you did it really quick, wouldn't take longer than 3 seconds. As I said, if we generalize that, we're taking the amount of numbers there are and multiplying it by n plus 1. For us, there were 100 numbers and we add 1, so that was 101 times 100. And obviously we divide it by 2, which in most of the formula booklets doesn't involve a division like a fraction, but they just have a fraction as a number at the front. Okay, so this is the formula for what this funny symbol is. This funny symbol is called sigma. It's a Greek letter. A lot of children who I teach in New Zealand don't really like the letters being in maths, but we all know why. And we look to Greek letters. And this means add up in a series like whatever's to the right. And there's a couple of things that come with it. If the number that we're using, or the letter, sorry, that we're using to find the sort of generalization of the series, or the sequence, is given generally as R, then we tell this this instruction is quite important. Like, where do we start? Usually we start at position 1. So if you've ever done nth term, sequences and series are very linked because the numbers in the series are typically a sequence. The difference is we're going to add them up. And this R, this number, this letter at the bottom, it's essentially the position. And we've got to put 1 in to an nth term, essentially. And how far do we go up? We go up, let's say we're going to go to the 3rd term. So it's not writing. It's not actually writing up there, so bear with me. Okay. I wonder if it's something else. Anyway, let's resume. And so I quite like this being up close. You can see it all the chalk. Let's get rid of that. So let's say we go to 3, and we'll get rid of that. And we are going to add up a sequence which is just made up of a single expression, like a single letter, which is R. Now, to get this into a series, all we do is substitute the R values from where we start, which is here, to where we need to finish, which is 3. So we put 1 in, we get 1. We put 2 in. Let's write it as a series. So we put 1 in, and we put 2 in, and we put 3 in. Add those together, we get 6. So the result of this is 6. Now, we just looked at methodologies where we can add them up with a formula if this number R is really is going to be huge, right? So, for example, if this number up here was, I don't know, something like 101, as you can appreciate, that's going to entail having to add up to 101, and we could write it out, 1 plus 2 plus 3, but actually instead we can write the formula that we have, which is a half, and however much we're going to go up to, which is n plus 1. Now, this here is saying that we start with the number 1, keep going, like keep adding them until you get to 101. It's just like our problem earlier when we had to add up to 100. So we just have to decide our value of n, and in this case, we have to add up to 101. So we put it in. And of course, this might require a calculator if you want to get it done a little bit more expediently. So I've just chosen a chalk on here, and it's so it's slow to actually write. So it's 102. Now we could half that to be 101 times 51, which is fairly straightforward. There's a little pattern to that, because you can say 51 times 100 is 5100, like 5100, and then 51 times 1 is 51. So it's like this really nice number, 5151. And as I say, you could verify that with a calculator, but that's how we understand the sigma notation there. We put it into a formula. Now there are some other situations we need to be aware of. For example, if we add up with 1. So let's get rid of just this. So if we have the sigma notation, and we start with, in fact it's the same as last time, we start with r equals 1. So I'm going to start with, and we go up to anything like, let's say 10. And let's say you have, we're going to add up 1, and we're going to add it up to 10. This gets a little bit confusing, because if you do it based on this one, we may be thinking, okay, we'll put r equals 1, 2, 3, 4 in. But really what we're saying is from, this is forming like a sequence where r equals 1 is the first position. And what you see is that this equals 1 in the first position because there's nothing to substitute in. So even if r becomes 2 for our second position, there's no substitution, so it's still just 1. And we keep going until we've done 10 times. And so you can see that's just that number added that many times. And so if we generalize that, whatever number's on the top, instead of 10, let's make it n. That's going to be what this one adds up to. And to be fair, that's going to work for most numbers, right? If you have 2, you're going to add it up in 2s, you've got 3, you're going to have 3s, etc. So there are some baseline rules, and so far the only thing left is if we have to add up a sigma. These are all the little rules that we learn, and you can prove them because they're series. I'll show you real quick for this one. We've got r equals 1, and we'll go to 3 again. But in this time we've got 2r. So it's really good to write this out full to see this one. So in r equals 1, we've got 2 times 1. That's our first term in the series, and then we've got to put the number 2 in there. We've got to keep going. So 2 times 2 is 4. So 2 times 2. That's always 2 at the front, but it's this number here that's changing as we go up. Okay, just be aware of that. And lastly, 2 times the 3, and that's where we stop. Now, what we can see is that there's a factor of 2 in every single one of those. So essentially, we could take this out as a factor, and we would have the sum of 1, 2 plus 3, which is the same as the r. So there is a rule that we can take out a factor, because we can't necessarily use that formula unless we do have this sort of basic. And let's say we're going to go to n now, generally. Well, fair enough, it is still 3, right? So let's make it an equivalence. This would be the same thing. So this would be if I had 2 on the outside of a bracket, and so the bracket's there, and then I did the expansion of the 1, 2, and 3 separately. So we're going to apply those rules to some of these, and the numbers aren't always nice, and we typically use a calculator for a lot of it. I'd probably invite you at this point to pause the video, to have a go at using those rules on what we have, and see if you get to the numbers that are at the bottom of the screen. And we'll now proceed, so pause, but if not, here we go. So for the blue one, we're going to be looking at rewriting this with a 3 at the front, and r. I suppose the other thing to note is that these can be split apart. So if you had 3r, which is sigma 25, that can be written as those two sums separate, because you're going to add up that amount of ones, whether it's part of the whole or whether you do it separately. It's still going to be 1 plus 1 plus 1 plus 1 over and over. So we can split them up like this. And we're still going to start with r equals 1. It's just going to apply to all of this stuff. And in a case which is 25, we're still going to 25 for both of these. I've also factorized out the 3 at the front, and so that just becomes a multiple of the formula, which is 3 times a half times n, which is 25, times 26, which is n plus 1. And then we're going to add this standard result. Now, when it was just a 1, it was just n, and n in this case is 25. So that's that, and let's see what this comes to. Let's do a bit of quick maths. We've got 13 times 3, which is 39 times 25, so we get 975. Not too bad. And we're going to add that final 25 to get to 1000. So was I really nasty? Probably not. Only had to get to the second answer to get that one. And it is very interesting because the amount of people that chose each one currently stands. So the people that have picked each one currently stands at 30% for the yellow, and for the blue 38%. Thank goodness it's more. 22% for the pink, and 10% for the green. So overall we have a winner. And do you ever know that game, Who Wants to Be a Millionaire? Let's finish that number off because it didn't seem to write. There we go. You know that game, Who Wants to Be a Millionaire? They've got the ask the audience, right? There's a whole theory called the wisdom of crowds. Would it apply here that if we had to ask a lot of people to just guess the answer, that the average would essentially verge upon the actual correct answer? It's very intriguing, and most recently I've seen it in a lot of different areas of statistics as to why certain things work. And you can possibly see it here. So if I've got a number of people and they do seem to tell me that they're guessing this stuff, then maybe that's why we have that convergence, and we'd have to seriously worry if the real answer wasn't the most. Something must be seriously wrong. We've done the blue. Let's look at some of the other ones because they're a bit more intriguing. I think the yellow one. So with this one, it doesn't start at, oh, it's got a rubber for some reason. But this one, it doesn't start at 1, and that does pose a bit of a problem. So everything is as it is before. The 7 can come out. Now it goes to 50. But this time it starts at 20. And we've got R. Okay, so all of that, absolutely fine. And with the takeaway sums, you're just going to take away 1 like a ton of times. That's fine. But I want to show you what happens with here. Since it's only from the 20th term, but the formula only goes from the first to in, so ideally this is not r equals 20, it's r equals 1, because that's how the formula works. We need to write this in a way that can be seen as from 1 to n only. It's quite creative how we do that. So I'll still keep the 7 on the outside, but what's on the inside can be thought of as the sum to 50 if we start at 1. And of course we know that that's way too many. That's all of them. But if we take away a certain amount of them, we have to start at 1. But if we take away, what would we take away? You ever think? Obviously you can pause the video. You should probably pause the video if you want some discipline. I can't have a pause long enough here, to be fair. It's not going to make great viewing. So if you did pause it, here we go. See if your suspicions are correct. We'll be thinking about here, we want to start at 20. So what's included in our summation is 20 onwards. So we want to get rid of 19 and below. So if we went up to 19 and then just took that away, what we'd be left with is the summation of that point onwards, which is 20 to 50. So that can be written like this. That's the crucial step. And after this point, you're just putting in values of in. So I'll take you through one more step, and that should be enough for you to carry on and do the rest by yourself, because it's really important that I don't do everything and leave something for you to walk and journey through yourself. So if I then put in the formula for the first part, I'm talking a value of n is 50 this time. We've got a half times 50 times 51. To be honest, I should probably put another bracket there because things can get a bit stickier. And for this one, we're going to go from 19, I should put times, looks better, looks clearer, times 20, which is n plus 1. Now close my ket. So I've got all of that. Put that in a calculator, do the sums, and it's definitely an expedient way to add all the numbers from the 20th term in a series to 50 for the nth term, 7r minus 4. It's pretty complicated notation when you really think about trying to explain it without knowing this mathematical notation. This makes it very clear and precise what you're talking about. Congratulations, anyone who selected the correct answer here, because clearly it was not the most clear-cut of questions for a lot of people. Appreciate you watching. I hope this has helped introduce you to the sigma notation. All right, thanks. I'll see you in the next one.